project and homework. All right, so some people may be wondering, so first of all, what is data mining? So when I first started teaching this class a few years ago, I was wondering this question to myself a little bit. So it's kind of related to machine learning. Is it just machine learning on large data? Is it really just statistics? Is it, how is this different from many other fields? And so it doesn't really have one good definition. It's kind of the intersection of several different areas. So what we'll try and be looking at in the class, one of the perspectives we'll be taking is, we're going to say, if you have data, what is it that you can recover, and also what can you not recover from the data? So we'll try and look at these questions. And this is in the computer science department. We're going to be looking at some algorithms of how to try and reconstruct these things. So maybe if this was taught in a statistics department, and when I was a graduate student, I took a day mine class that was just in a statistics department. There was much less emphasis on the actual algorithms of how to compute certain things, but more of was the property of the data. And maybe it was clear there was some way how to compute it, but it wasn't necessarily very efficient. So we're going to be looking, balancing the efficiency as well. And so more generally, it's going to be about how to think about data analytics. Okay, so maybe data analytics doesn't mean anything either. Maybe this is just another buzzword, but it's how to do analysis on data. Okay, so this is kind of a very broad subject. It touches every area that actually has data, and so this is a very challenging task. And so we can't cover every single technique. We can't cover every type of data. But I'm going to try and give a philosophy throughout the class with highlighting many different classic techniques, and give a general philosophy of how to kind of look at this data and to how to analyze it, how to think about setting up your pipeline of the analysis. So if you come back to this discussion we had before, you can think of this as kind of balancing two parts. One is maybe on the modeling side, where maybe you would put statistics entirely on this modeling side, where this isn't entirely true, but some people in statistics don't maybe care about the efficiency or the algorithms or the construction. They'll say, here's some property that the data has or that we can find, and maybe there's some brute force algorithm, but let's not worry so much about it. Whereas if you took a class in algorithms, you have these very well-defined problems, and your goal is how fast can you solve this very well-defined problem. Okay? And there's lots of techniques there. And so then both machine learning and data mining fit somewhere in between. It's probably not a complete one-dimensional line there. There's probably various other things that you would separate them. But the way this is kind of taught and how it's typically taught, at least here at Utah, is machine learning is a little bit closer to statistics. In data mining, we'll be talking a little bit more about the algorithms, and we'll really be focusing on this interaction between how correctly can we model the data and how efficiently can we process the data. And so sometimes you actually have to, in doing this, make some compromises on the modeling. You're not going to get everything right about the data. You're going to have to throw away some information. But you're going to do this so you can actually do some computation on it. And so a lot of the class will focus on, extremely large-scale techniques for processing this data. Things that are scaling. If you've heard about these buzzwords like big data, we're going to be, focusing on this end of the spectrum, that things that will work on the big data and will continue to work on big data. There's some techniques we won't cover which aren't really as scalable, so we'll focus more on the scalable techniques. And so sometimes, yeah.
Is it possible for the slides to be larger?
So has anyone had classes in this room before. They've done. I've never taught in this room before, so I don't. Are the slides usually this size up here? Yeah, or it's been larger before. Okay, so. So you think it's the resolution. Let me try mirroring. So it's 8. Let me try.
Just barely got bigger when you did that.
Yeah. Okay. So my. Okay, well, it's bigger. So bigger is not always better, I guess. So let me try unplugging and plugging back in again, see if it magically fixes it. And, all right, that looks better. All right, okay, good. Better, all right. Okay, so, all right, so back to what is data mining. So it's also true that if you take data mining at a different university, or maybe there's another class at this university that's called data mining, it's probably going to be taught differently. So I have colleagues at different universities who teach, data mining that's is very different than how it's taught here. So how it's taught here. So what is kind of the flavor of it in this class? And part of the reason for this is to fit in to the general spectrum of the other classes. So we don't say have too much overlap with machine learning. So as I said, we're going to focus on very large-scale data and the techniques which scale up to those. I'm going to try and do a broad coverage of different techniques, but I will also touch on a lot of more advanced recent developments. So some of the things we'll be talking about were developed in the last, entirely developed in the last 5 or 10 years. We'll be talking about papers that actually came out in the research community in the last year. But we'll also try and cover all the classic techniques so you have the broad background. And then the things I'll focus on are the things that are new improvements and are currently the state of the art in certain areas. But it's impossible to cover every single technique, so we can't do that, but hopefully you'll get a broad picture of the different techniques and this brings us to the next point. So the goal will be to do things fairly formally, and I'll try and present things that are fairly general and high level, and then give kind of the classic techniques, and then I'll try and specify things forward. So by formally, I mean I'll try and define things precisely, and occasionally I'll state formal theorems about things occasionally. This is not going to be a class that's going to be full of proofs. I think there may be a couple of very small, cute things. I'll prove something. Usually they'll be like 3-line proofs. They won't be too complicated. And I'll mainly try and give intuition of why things are true. But even though we're going to go and look at all these formalities, this is not kind of a theoretical computer science class. I'm focusing on things which are actually used in practice. So there are lots of more beautiful theoretical things that when I initially started thinking of teaching this class the first time, I thought, oh, these are very beautiful, and I wanted to teach them. But then started discussing with people who are using them, trying them myself, and they didn't actually work as well as some other techniques. So we'll stick to things which are in the middle here, which are both very nice to define, and you can say something very formal about them, but are also useful in practice. And often, the use cases that I'll be thinking of are often motivated by these large internet companies like Google and Amazon. And so I have some of my colleagues that I know and work at these companies and actually are using some of these techniques. So they have lots and lots of data, so this is why this is on the large scale side. So we'll touch on some classic things that don't necessarily scale quite. And so we'll also tend towards more probabilistic algorithms. So these have connections to both computer science and statistics. So when you first see these randomized algorithms, they can sometimes seem very intimidating. But typically what it means is the algorithm is actually be a lot simpler than if you're doing something that has no randomization in it. It's just the analysis of it is going to be harder to get very precise, and even sometimes to say precisely what the actual meaning of it is. So we'll describe these algorithms, and then I'll give intuition of why they're true. In fact, the first couple of lectures, not counting this one, are actually, the whole goal is to give you some intuition on some very basic ideas that these probabilistic algorithms will use. So we're going to talk about some types of hashing of data. I'll describe in a bit more detail soon. And this really is meant to give a lot of intuition. And most of the proofs use something, analysis similar to what would be used if we were to prove the techniques we talked about the first couple lectures. So if you kind of get the intuition there, hopefully it'll carry over to the rest of the class. So though I'll mention when I first started teaching this class, I taught maybe an extra 2 more lectures were focused on more probabilistic algorithms. But as it turned out, people have come up with simpler and ways that work better, which didn't necessarily need the randomness in some cases. So the class has maybe moved, and maybe the field in some ways has moved away from this a little bit. But I'll mention this as we're at those parts of the class. But there's still kind of some very cool ideas in here, and hopefully, if you haven't seen these before, it's not going to be too intimidating. We'll go through them, and they'll actually be fairly simple once you start seeing them. And we'll see and again, we'll see a few tricks over and over again. So if you don't get it the first time, hopefully the second or the third time we use a very similar trick, it'll start to make sense. Okay, and just to be clear, we're not kind of learning specific software tools. I'm not going to focus on specific programming languages for doing data mining. This is more about the general principles behind it. You'll have assignments where you have to program something, but it won't be specified to using one package. Some of the things you'll have to program you probably could do in certain packages, but I want you to learn more why it works and explore the guts of it, so that if you run a package and you see it works or it doesn't work, you know maybe why that is the case. So you aren't limited to what the package does. You have a more fundamental understanding. I assume if most of you are in a advanced undergraduate level or graduate level computer science class, you can figure out how to use a software package. What you need to figure out is which of the commands to use, and if it works, how to interpret it, and if it doesn't work, understand why it doesn't work. Okay, so we're going to go more of the fundamentals, not the specific tools of how to use things. Okay, and so this class, it's going to have some math component to it. There are a handful of people from the math department taking the class, so other of you don't have as much math background. The key tools are going to be from linear algebra, from probability, and actually from high-dimensional geometry. I'll assume a little bit of background in linear algebra and probability. You should know what a matrix is, although I'll redefine it and give some examples and kind of how basic matrix operations work. And in probability, you'll need to know basics like what a random variable is, concepts like linearity of expectation. We'll start with these basic concepts, and then we will define from there some really cool algorithms that use these techniques. I won't expect too much knowledge in high-dimensional geometry. We'll touch on various parts of it throughout the class, and I'll try and explain things from first principles of that. The reason to use the high-dimensional geometry is because then you can draw some really cool pictures to understand things intuitively. I'm a very visual person, and hopefully I can convey some of that visual intuition to help make some of the kind of more complicated concepts make sense. All right, so here's kind of a high-level outline of how the class will work. This is not an exact structure. This is one way of thinking about it. We'll start by looking at some statistical properties and kind of understanding some very basic random effects, basically the effects of hashing and how these hashing and collisions work. And then we'll look at data and distances. And so it seems very basic, but every technique really needs to be built on some notion of either a distance or a similarity between two objects. If you don't have this notion, then it's hard to do anything else. And so we're going to start here and define these concepts and give examples with lots of different sorts of data examples. And then this is very related to clustering, which is basically aggregating things which are close to each other. And we'll define this more precisely. And so then this will lead into ideas where you can then start finding structure in data, such as clustering or regression, which is kind of, in general, these patterns in data. Often these are these linear patterns in high-dimensional data is one way of thinking about them, but there's more general things you could do. We probably won't touch too many beyond those. And then there's also finding kind of some anomalies in data, looking at noise in data and how this affects it. And maybe this link analysis part should be in the structure. I don't know. So then the last part we'll be looking at this noise and the uncertainty in data. We'll talk about how this affects various things. And one other thing we'll look at is the structure of these large graphs. So so for a long time, graph theory was really a fairly theoretical topic. They were very hard to collect large graphs, and a lot of the phenomena happened at the small scale stuff people could understand, but we're much used to it. Now there are very large graphs because of these, because of the web and because of social networks. We can collect them, we can analyze them, and there's a lot of rich information there. So we'll look at some of those, and we'll look at ways of summarizing data. And summarizing data has to do with noise and uncertainty, because when you don't have all the data in your summary, there's some uncertainty in what part is not there. So these are kind of some ways of grouping the class. I'll show you the web page schedule, and you'll see a different way of understanding it. Okay, so what are these statistical principles that we'll start off with? So what we want to do is kind of see what happens when we're generating data with replacement. So if you've seen a hash function, or you've hashed data, you have a bunch of bins that you've heard of this like balls and bins problem. We're going to throw balls and bins with replacements. And so you want to do this where you have maybe a really large number of distinct items. These could be IP addresses, words in a dictionary, edges in a graph. And so you want to see what happens when you start throwing these balls in, and what kind of phenomena happen in here. So this first part of the class will be kind of probably the most abstract, aside from a few basic lectures before I get into some things. And so, but will turn out to be a very useful tool in many areas, and is really of growing importance. So the first thing is, if you keep throwing these balls in the bins, when do they collide? When do you get two balls that wind up in the same bin? How many times do you need to do this before this happens? Right? So if you ever build a hash function, this is kind of an important event. If you have to deal with this in a special case. The next thing is if you keep throwing these items in, when do you have a ball in every single bin? Right? So I kept throwing items until there's finally this bin got filled in and every bin has been covered. Okay? So this is another kind of critical event that happens. And then finally, when do they all roughly have the same number of balls in all the bins? They're never going to have, after they all have 0, they're never really all going to have the same number of bins. Then when does this kind of sampled approximation of this distribution give a good estimate, essentially is what it's saying. And these are kind of the 3 levels, and they're kind of, these random effects are used in various different algorithms. And so we'll kind of look at these bounds and kind of give the intuition behind them, and then later in class when we have randomized algorithms we can see, oh yeah, this was one of these 3 bounds. One of these 3 things was happening, that's why this algorithm works. So we'll kind of pre-process our intuition for several algorithms in class. So then after we do this, we're going to kind of back up and talk about various types of data. And one of the kind of, this is probably the most important slide or most important thing to actually get out of the class. And that is that when you do data mining, there are all these algorithms, all these techniques that are defined to work in general on lots of different problems. Okay, so you want to get, but in order to do that, when you actually get data, it's often going to be extremely messy. It's not going to look like the input is supposed to be for the problem we're going to learn how to solve. So we're going to need to take some messy data and some weird structure and get it into a form that we know how to run an algorithm. Okay, so I've tried to, kind of one of the key ideas is to take data, and this could be text data, it could be graph data, matrix data, kind of data from a table, and somehow convert it into kind of points in some space, maybe some high-dimensional space. Often we're going to be convenient if it's actually high-dimensional Euclidean space, but if it's some sort of metric space, this will work. And if you don't know what this is, well, we'll go and define these terms. So you want to take your data and define it in this space, and then once you have data in this form, there's all sorts of algorithms you can immediately apply. And so if you can apply them, then they're going to run in a certain way, a very, very predictable way. But given that your data is in this space. Okay, but your data is not these points. Your data is text or is a graph, right? So when you do this conversion, you're probably losing something. This is modeling of data, right? So how do you model in some abstract representation? Sometimes you'll go, say, from a graph to a matrix, and you'll stop at the matrix. Sometimes you'll go from the matrix to points, and you'll think of it in points. But you can run some algorithms on other forms, like a matrix is another general form that is well studied, and there are algorithms just for matrices of data. There are algorithms just for graphs of data. So sometimes your goal is to build a graph, right? So if you have all the data of Facebook, one thing you want to do is if you build a graph of the data, who's friends with who, each person is one of these nodes, so there are like over 1 billion nodes in the graph, and an edge is if these 2 people are friends with each other, they have an edge between them. So then you immediately have a graph. You can then run a bunch of algorithms that we know how to run on graphs that we'll discuss in class. But is that the right way to define the graph if they're friends with each other? Well, that's one way of defining an edge. Maybe you want to say an edge if they've commented on someone else's wall, even though they're not friends with them, right? There are various ways of defining these edges, and these choices will affect your outcome. There's not one way to define the graph of the problem. There's not one way to define these points, and so we'll have to talk about what are these different ways and what are these trade-offs and how does this affect things. Once you have points, then you need to define the distance between the points. Which distance you choose will affect the outcome as well. So you need to make a modeling choice of the right distance between the points. So we'll discuss various sorts of distances and how they relate. Some distances are much easier to work with. So Euclidean distance is one of the easiest distances to work with for a lot of algorithms. You can run very efficient algorithms. but it's not always the best, not always the best modeling choice. So, and so one of the first things we'll talk about is how to go from text into something that you can find an abstract distance over, and we'll talk about the various ways you can convert from text to some abstract distance. If you take a natural language processing course, you may touch on this, but then you'll say, well, when you do this, you're really losing a lot of information, and that's true. But if you want to scale up to enormous size, the techniques which don't throw away this information have trouble scaling up. So we're going to be more focusing on the large scale end of these. If you want the natural language processing course, we'll talk about things that are maybe not quite as scalable, but focus more on the modeling of text, for instance. So it's another example of the trade-offs we've made in this particular course. So, you know, one of the most basic problems once we've gotten to some abstract setting where we have points in a space and we have a distance is we want to say, given some large set of points, these could be some customers we have, or it could be some events we've observed on our web page. Have we observed this exact same event before? Is this customer exactly in our database? Can we return that quickly? And if that's not true, maybe we want to find the closest customer, right? The most similar event that we've seen before. And if we've defined some distance, some distance and some space, then we can immediately apply a variety of algorithms. And actually computing the closest point is going to actually be, you know, it's not hard to do, but it's not efficient when P is very large. We're going to want to be asking these questions over and over again. So we're going to define some approximate ways of doing this that are guaranteed to get the closest distance, but we'll get something that's close. And actually, since our distance was a modeling choice anyways, it probably shouldn't matter so much. So we'll talk a bit more about these trade-offs. Okay, so then this leads next to, once we have a distance or similarity, and you have data in some space where you can define this, you can start defining these clustering algorithms. And then clustering has a lot of other, you know, this is kind of the classic problem in data mining is clustering. And there's many different clustering algorithms and ways to define it, as there are people who've used, you know, some sort of data mining software. Right? Clustering has so many variations; it's impossible to even keep track of. So we'll focus on some subset of these and try and look at some kind of very broad classes, some very kind of classic examples, and also some that scale to very large sizes. And some of the things are, given a cluster, do you need a specific representative of the cluster or not? Can the clusters overlap? Can a point be in more than one cluster? You know, what kind of properties does this clustering give you? And importantly, you know, how efficient are these algorithms? So I guess the plan is to look at three kind of general types. The first is this hierarchical clustering, or sometimes called agglomerative clustering, where you're kind of growing these groups from individual points into kind of larger classes of points, and you keep growing them up, from each other and joining classes together. And you have lots of kind of modeling choices about how do you choose to join two classes together? How do you choose to step? Then we'll talk about these classes of clusterings, where the most famous one is k-means clustering, which I'm guessing many of you have heard of. But there are others in this class, and some much more efficient, some much more robust in different settings. And these have the property that they have a specific representative from each class that they have. And there's nice kind of geometric intuition, nice algorithms, and variants of these that scale to much larger data sets, but have some of the kind of nice properties which made, for instance, k-means clustering so popular. And then the third type we'll touch on is graph clustering. If you have a large graph of data, how do you break the nodes down into different classes? So all you have is this edges connecting the nodes. So you kind of want to have as few edges as possible going between the different classes, right? So if this is a graph here, you want this to be one cluster and this to be another cluster. And so we'll talk about some basic classes of these, which are called these, like this, one of the ones we'll talk about is these spectral algorithms for units. And this intuition actually comes from thinking of the graph as a matrix and then using the matrix structure to define the cluster. Okay, so then one of the other things we can do when we have this data in some space is we want to find kind of other sorts of structure. Instead of breaking into groups, we want to find, say, some coherent pattern across all the data. And so, this is a general class of things called regression. You may have heard of, the most commonly used in just two-dimension, you're fitting a line to data. Maybe you're fitting a parabola or a polynomial to it. This is one form of regression. We'll talk about this, and then we'll talk about some generalizations to when your data is living in a higher dimensional space or a more abstract space. And here's another place where we'll need this view of this high dimensional geometry. And so one of the intuitions that we'll try and gain throughout the semester is your data in this high dimensional space, and you want to fit, like if I'm in three-dimensional space, you're going to fit a plane through the data, with that all the data is close to this plane. But this kind of be more general if you could be in a 100-dimensional space and fit a 5-dimensional subspace, linear subspace through the data. And that's essentially what these algorithms are doing, but they're usually written down in other ways. And we'll try and build up why these algorithms work and what they're doing through some of this geometric intuition. And then we'll talk about some variants of these. Let's see. So we'll talk about kind of this L2 regression and PCA approaches. There's other things called multi-dimensional scaling, which is very close to the same thing here. It just slightly changes how the input is given just the pairwise distances instead of a representation of points. There's a cool technique which has been very popular and has won kind of some research awards called the random projections technique. And this is it's the easiest to implement, and seems very scalable, and has some very different sorts of bounds and different trade-offs from these other techniques which have been around for a lot longer. This is a much younger technique. Say PCA dates back to maybe the 1930s. The earliest probably the 1970s, but really popular in the last 10 years. There are other versions, like there's an L1 form of regression, which is more robust to outliers than the typical L2 version, and we'll talk about what L1 versus L2 means. And so we'll maybe get into a special topic on compressed sensing, which is where your data has, there are different notions you can define, like the sparsity of the data and special structure in the data, and it can take advantage of special structure to recover things that regular, say, like Gaussian elimination was not able to recover if you don't assume this special structure. And this has been kind of this amazing wealth of new algorithms and techniques based in the last 5 or 10 years that have influenced how we're doing sensing data, say, for medical imaging and taking pictures with these telescopes where certain operations are extremely efficient. We want to minimize certain sensing costs. So this is a really cool new topic that I'll probably have a lecture on. I won't be able to cover everything, but I'll give you a sense of what it is and kind of very basic algorithms that will work in a lot of cases. All right, so then so one of the things we talked about here, kind of in both this L1 regression, which is kind of a more robust form, and this compressed sensing, which is actually able to kind of, one of the things it can do is kind of remove away all of the noise magically. It can somehow recover things exactly from seeming noisy data. So what this means is that you have a really big issue is in large data, and this is, maybe a strange concept, but when you're automatically sensing data, when you're automatically gathering data using these algorithmic techniques, or you're able to, say, have users generate data, right? This is how a lot of the data on the internet is found. It's automatically done. It's not someone human is writing down very careful things in a lab notebook, and then they're typing them into Excel. That also has errors in it as well, but if you check over it a few times, you can often catch a lot of these errors and identify things as outliers. When you're doing things automatically, it's a lot harder to do this. You know whether something's an outlier, whether it's noise, or whether it was a problem in the sensing of the output. It's like almost impossible to know whether something was noise or that was just something that you didn't expect. So this is kind of a pretty important topic, and there's lots and lots of techniques trying to somehow deal with it. So some of them are finding the core structure, and then what is not in the core structure is probably noise. That's one general technique. There are lots of other techniques saying, I'm going to try and find all the outliers in the data and identify them by some way. And I'm typically skeptical of these techniques in general. I'll kind of give kind of a broad like a manifesto of how to deal with outliers at some point. So we'll have some discussion on this, as well as kind of some ways of how to exploit noise in data. There's new techniques in one of the flip